All right, so we're in Section 4, Week 2. We have 3 more classes, and then we'll have a quiz on Section 4 on the 2nd. And we are currently in the karting program. And we spent most of our time on this script, which happens to be kind of the biggest script. We did start with the keyboard input, I will say. And we hunted around the game object hierarchy to understand how everything is connected. And here we are in ArcadeKart. All right, so we stopped off. We were kind of getting deep into this move vehicle method, which I believe was coming from the update. Method let me just pop up here. Yeah, so fixed update, sorry. So heavy with physics. And let's see, so gather user inputs. We're kind of seeing if the vehicle is grounded or not. We have to look at each tire and see if any of them are grounded. And here we have ground percentage, air percentage. And what happens here is if we can move, if we can apply physics, pretty much if the game is active and the cart is running, then we have to call move vehicle. And we're going to pass in from the user input if they're accelerating, if they're braking, or their turn input, which goes from -1 to 1. And so move vehicle. So it's down here. And this is kind of like the largest part of the script. And I kind of went through here. We're figuring out, are we moving forward? Are we going backward? How much force if we're going forward or backward? What's our kind of our acceleration power, max speed, if we're going over max speed, if we're braking. So it's definitely figuring out a lot of like what is the current state of this kart in physics. And let's see, how much turning power is happening? Should we be entering into a drift? How much of our turning angle is currently happening? Yeah, right. So, has collision. I remember this. It was I thought it was, are you colliding? But it's actually like, are you touching the ground? That's basically what's happening. So at least is one of your tires on the ground. So is ground percent greater than 0? So is one of your tires touching the ground? Or is there some type of like with the bigger collider, can we determine if we're touching the ground? And then we kind of, if that's a 1, then that means we will multiply with all this, otherwise it will 0 out. And right, figuring out based on all that what type of our new velocity will be, and should we clamp it? Is the numbers getting too high? What type of range are they going to go in? And coasting is when we aren't touching. Okay, right. So coasting means we still have some acceleration, but we're not accelerating. The user's not either trying to accelerate or brake. And we should just be moving forward, but kind of slowing down. So this is that move towards, like vector 3 dot move towards. So calculate a position between 2 points, like where we currently are and our target where we would be going. And just like how far along, very similar to like that blurb in between A and B, like where are we T. And drifting. So if ground percent is greater than 0, we have at least 1 tire on the ground. So if we are in the air, that means we just landed. Like this was true, but the tires hit the ground, so we're landing. I don't know why this is handled I don't think it's handled in drift. I think it's handled in the fact that at least one tire has touched the ground. And if that's true, let's just double check that we haven't just like left the air and come back to the ground. And here's a little different. It's not velocity; it's angular velocity. Angular velocity is velocity is like how much are we moving between two positions? Like how much is our position changing? More of something that you're familiar with, like a velocity of movement. And angular velocity is a movement of how much are we rotating? How much difference in like the degrees of our angle where we're pointing? How much is that moving? That's angular velocity. So dealing more with steering and checking if we're like currently in are we going in reverse and like our steering needs to be. So what happens is if you're pressing left and you're moving forward, you want to turn to the left, and if you want to move to the right and you're holding right and you're moving forward, then you hope the car moves to the right. But when you try that in reverse, you're going backwards. Actually, if you're in reverse and you're steering to the right, you're going to turn the car left. So anyway, the steering gets multiplied by -1. It gets flipped. And I think, let me just double check mine. Oh, no, sorry, 504. I thought this was new code. So we were wrapping up last class, moving through here. And then we're taking the angular velocity from our rigid body, our physics rigid body, which has calculated some stuff the last frame. And then move the y angular velocity towards our target. Move towards, so math F, just one number, a float, move towards. Take our angular velocity y, move it towards this, whatever this gets calculated to. And by this much, how much of a frame, a fraction of a second happened since the last time we ran. Fixed update multiplied by this number here. Okay, so if you remember, y is the axis that points up. So y is actually really important for us rotation-wise. Remember the green circle here? This is like our angular velocity we're really interested in, because this is the angle that we're turning at. So that's why everything for angular velocity, everything's y, more or less. All right, and then 504. So this is where we ended pretty much. All right. Rotate rigid body's velocity as well as generate immediate velocity redirection manual. Okay, float velocity steering was 25. All right, if the cart lands with a forward not in the velocity direction, we start the drift. If the cart lands with a forward not in the velocity direction, we start the drift. Okay, so if ground percent's greater than 0, so if one of our tires are touching the ground and our previous ground percent was less than 10%, so we're not on the ground last frame and we're on the ground now, so the cart is landing. So for landing in our forward directions, not in our velocity direction, we'll start to drift. Okay, but I mean, this right here is just telling me that I'm landing in this if statement. So vector 3, project on plane, which we've covered before. Take our velocity of our rigid body, and then what's the plane? Our vertical reference. Okay, I guess that's just y up. Let's take a look. Yeah, vector 3.y up. So they just have like a constant for it, sure. 504. So basically project onto the y plane. So a flat plane, like a floor plane, basically get rid of any velocity that's going up or down, and then normalize it so that it's like a unit-sized vector. And so that's what we're calling a flattened velocity. So basically just know like what direction, what's our direction of our velocity, and just the x and the z, and not even like the strength of it, just normalize it. And then we're going to do the dot product of the two vectors. So whatever this flattened velocity is, we're going to dot it with our forward. So remember, our forward is like our local orientation. So wherever we're rotated and pointing forward, our blue arrow, which it can be, is not, based on our own local rotations, it might not be aligned with worlds positive z. So it tells us our forward. And multiply that by going to the math library, get the sine function. Okay, so it's not, I thought it was sin, so sine and cosine, cos and sin. It's not. It's, give me the actual sine, like forward, backward. Okay. So basically it's saying accelerate input is a flow. Like if our acceleration is forward, we're accelerating positively, we're moving forward, this would return, I'm going to assume that it returns like a +1, but let me just take a look at that. This is interesting. We have some examples. I just kind of wanted to, that's cool that they have that now, but I really just wanted like the documentation. I'm going to look it up real quick. So I'm not sure what this float is that it's returning, and usually you can just point me right to the documentation. Returns a value of 1 if f is 0 or greater, or -1. Okay. Yeah, so just returning +1 or -1. So if we're going in reverse, this will be -1. If we're going forward, it'll be +1. So if this is less than, now take the cosine. So this is a trig function. Take the cosine of angle f. And take the min angle to finish our drift. Okay. So I'm going to have to go over cosine and sine with you a little bit. Trig is like another one of those little areas besides like just understanding vectors. You just have to understand some basic trig. The higher the angle, the easier it is to regain full grip. Okay. So it looks like the min angle to finish your drift. So if we're at an angle of 10, then we can regain control. We can come out of our drift, I guess. So if this was 20, the easier is to regain full grip. So if it's at 20 degrees, it means we have to be at 20 degrees to finish our drift, or 30. All right. So I'm guessing that there's the angle difference between like your thrust, your velocity forward, and the angle to like where you're currently pointing. Remember, your transform dot forward. So if you're like moving, if you're angled differently than like the way your velocity is, this will aid in going into a drift. So sorry. Okay, here we are. So this is saying, yeah, I'm gonna look at that in a minute, because here it's multiplying by degrees to radians. So this is saying 10. So 10 is well, first off, 10 is in degrees. So radians, I could tell that 10 wouldn't be in radians because that 10 is past a circle. So one thing I was talking about was radians last time. So and like 1 radian, 1 unit is a big move. In fact, it was something like 57 degrees. Say here, 57.3 degrees. And that means basically the radius of a circle, which is this right here. How far along the circumference can we move based on how like the distance of a radian? How much does that cover of the circumference? And it's about 57.3 degrees. And if we see here, for a full rotation, it's 360 degrees, but it's only 2 pi in radians. But it's still a full circle, but it's just 2 pi. If we walk the radius, if we walk it times like 2 pi, if we take the radius and multiply it by 2 pi, that's how far the circumference is. And so we see here it's like 1, 2, 3, 4, 5, 6, and then a little part, right? And pi is that 3.14, blah, 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 blah. So, 2 times 3.14 or something is like 6 and a bit, right? So I know that 10 wouldn't make sense because 10 is past like a full circle. So, this must be in degrees. And then I also see that there's a conversion here, degrees to radians. So that also gives you another hint that this was in degrees because we're converting from degrees to radians. So MathF has, that just comes out to be a constant. You see it's just that number. So we multiply it by this, and we take the cosine of that, and if it's less than this. So what's happening with cosine and sine is cosine. Okay. Just for where we're currently at with this, one thing just to note is that when we talk about cosine and sine, what we're really trying to figure out is as we move about a circle and we're trying to understand like, oh, we're at so this we know we start at like 0 or 360 here, and then we move around 90, 180, and 270. We're trying to say, what's this angle? So if we start here, this angle 0, and this would be angle 90, and this is angle 180, 270. And if we have like, which is pretty easy to figure out the position, right? Because this is just like 1, 0, 1, 0, 0, 1, negative 1, 0, 0, negative 1, and so forth. Like we can figure out our XY positions on that. But if for any other angle, it's too difficult. So like if this is an angle of like 57 degrees or 42 degrees or whatever, how far out in the X and the Y is it? We don't know that. So that's what cosine and sine are used for. So basically we have this. We have like the hypotenuse, the adjacent, and the opposite. So what this means is like how long is X here? How long is Y here to get to here? And we have a hypotenuse of 1. We have a radius of 1, which is usually it's always 1. So we know that the radius is 1. We're sitting at this point on the circle. And like normally you might say, oh, I know my X and Y, but what's the angle here? Or usually we have is, oh, we know the angle, but how big is X and how big is Y? And just to know that X always goes between negative 1 and 1. And so here's negative 1. This is 0. That's 1. And Y always goes negative 1, 0 to 1. So they're always fluctuating, always moving back and forth. That's why we deal with these waves. The numbers for sine and cosine always go up and move up and down between negative 1 to 1, which I'm surprised they don't. Yeah, like here, we can see our waves here. This is the sine wave, this is the cosine wave. So cosine is really measuring oh, I lost my nice little graphic I liked. One second. It was in the circle. Oh, this one will do. So cosine is really measuring how big is x based on an angle, and sine is really measuring how big is y for a certain angle. So adjacent, hypotenuse, adjacent, opposite, and this is hypotenuse. And you can see it here, adjacent, hypotenuse. So as we move around a circle at certain angles, usually in we think of them in degrees, but I'm not sure. I think we'll take a look if they have to be in radians or degrees. But what it's saying is, okay, take that min angle. We know it's 10 degrees, right? And then it looks like we have to convert it to radians when we pump it into the cosine. So it returns the cosine of angle F. It looks like angle F has to be in radians. And then the return value will be between -1 and 1. Because, as I just said, x can only be between that. So it looks like we're looking at what is 10 degrees, so a really small angle. And then, so a really small angle is going to mean a large x, a large positive x, and like a small positive y, because we're in this top right quadrant of the circle. But what that number is, I don't know. But it gets calculated here. It looks like it, once I'm guessing this min angle to finish drift doesn't change. So, maybe this could have been calculated once, like in your wake or something. But maybe if it's exposed in the inspector and people are changing it, maybe you want to calculate it all the time. But anyway, this is going to eventually evaluate to some type of, remember this is the x value, it's going to be some type of large number less than 1, like 0.8, 0.9 or something. So now that we know what this will come out to, we're saying so we're dotting. So all this is within a dot method. Let me just make sure. Oh, no, sorry. If this dotted is less than this, then we say that we're in a drift. Okay. So if we dot our flattened velocity, so wherever we're like, the car is currently, getting velocity, and we're just concerned in the x and the z. If we dot it with our transform of our car, our forward direction, not the velocity, just where our car is currently pointed, and multiply that by, if we're accelerating forward or backward, this will just be a +1 if we are pressing down, and a -1 if we're not, and even if it's 0, it's going to be a +1. So even if we're not accelerating, this is going to be a +1. All right. So whatever our forward direction is, we can flip it. So this is a vector 3 multiplied by a float. So basically, we're pointing wherever we're pointing. Right, here's our front, our forward. If we're accelerating or not accelerating, it'll still point this direction. If we're hitting our brake, we're going to flip it. It's going to be multiplied by -1. It's going to point behind us. All right. So that's what's happening here. And we're going to dot that with whatever our velocity is. So if our velocity is moving forward, and let me break out my annotation tool here. Remember the dots. So if our local forward's pointing up and we're just pressing up, or whatever combination of our velocity mixed with turning and accelerating, whatever state of the velocity of the car was last frame, if they're pointing the same direction, remember when we dot this will be a +1. And if, I guess let's just argue with, okay, let's say our cart is pointing forward, our velocity is pointing forward, but we're holding back on the keyboard, right? So if we're holding back on this keyboard here, this will point in the back, but we're still velocity is going forward, this is going to be a -1. And we might have another case where, let's just say, should our let's just say for what somehow we're in some type of turn or something, or something's crazy. Let's just say our cart is pointing this way, but based on all the calculations on the velocity is pointing up this way. This is a dot product of 0, right? So in the other case, this part of the if statement will evaluate to something between +1 to -1, anything in between that. And I just drew the situations here, right? So now I got to get out the annotation tool. And if that, whatever that dot product comes out, if that is less than this, then this if will be true, and we will say, okay, we are drifting. So if the cosine of the angle, this is a small angle, remember, so 10 degrees. So this cosine is going to be large because this is dealing with the x. So this might be something like 0.9 all the time. So this is saying, okay, if this thing ever evaluates to less than 0.9, then we're going to be drifting. And the dot gets less than 0.9 whenever the two arrows are not pretty much lined up. So anything with, like, if we're happen to be pointing this way and our velocity happens to be doing that, and this might be something like 0.8, then we're going to go into a drift. Or this, we're going to go here, and this looks like is drifting. It's set to true. And you can change this number up in the inspector. If it's like too easy to enter into a drift at this 10 degrees, then you would update it, get 20 or 30 degrees going, and that this cosine from it would drop like 0.8, 0.6, 0.4, whatever. And it would be harder to like put yourself into a drift. So anyway, if this is true, I know that was a dense line there, and I had to go into radians and cosine and sine. Let me know if you need me to go over any of that. The dot product was involved, the projectile plane. There's a lot going on here. So let me know if you need anything. All right, so is drifting equals true? In our drift grip, whatever this field is, this will be our current grip because we just started entering the drift. And our drifting turning power, okay, these are just this. I guess these are like the starting conditions when we first enter into a drift. So if we're not drifting, okay, it's called drift management, but it says only if we're not drifting. I guess, but here's is drifting. So if we're drifting, we'll do this. If we are drifting, if we're not drifting, we'll do this. If we are drifting. So since like it's a little weird that we're checking the same bool, so this should really be an if else. Usually when I see an if and then another if, we're like doing checks for different stuff, but this is just checking the same bool here. So if we're not drifting, and if wants to drift, or we're braking, if either of these are true, if we're braking or wanting to go into a drift, however that's calculated, and the current speed is greater than our max speed times the min speed percent to finish drift, then if is drifting is true. I think all these variables that say finish drift, I think he meant to say like starting drift, because they just seem to be dealing with starting drift. Anyway, if we don't have to be drifting, but these situations happen, then actually we can enter into a drift as well. And it looks like a little different drifting power based on that condition. And we get some drift VFX going, which I don't know why they don't implement it here, because we're about to go drifting there. But in either case, then we can check again. Okay, because if this happens to set drifting true, then we can actually go in here too. So there's a situation where we can enter this if, that'll get set true, and then we enter into this if as well. All right, so get the absolute value of our turning input. So basically, it's saying, hey, are we turning it? It doesn't matter if it's negative or left or right, negative or positive. Just do we happen to be turning at all? Is all we really care about here. So take this turn input absolute. If it's less than our null input, meaning null input means there's a little bit of like a dead zone, like when it's 0 or even 0.01 on our registering our turning input. So on a keyboard, you're not really going to get that, but on a gamepad where it's like touch sensitive, where you can get values between 0 and 1, he's saying, hey, that they're like slightly, ever so slightly touching the gamepad. That doesn't qualify as a turn. It's with that null input, killing it with these small values. But anyway, if this is less than that, this means like they're not turning at all. And so if you're drifting but you're not viewing any input of a turn at that point, then they're changing the drifting power, move towards. So it's like whatever our drifting turning power is, it's starting to move towards 0. And how much is it moving towards 0? Well, we have drift dampening factor. So dampening in physics is like something that is slowing down. So in this case, we have a factor like a drift dampening. It slows down our drift times this small little fraction of a second that just happened. Clamp 0, 1. This means clamp whatever the value is. We don't even have to do a min max of 0, 1. It's just such a common thing that it'll clamp 0 to 1. Update the turning power based on input. Okay, so take our steering factor, our field. There's a float. It's coming from our final stats. Remember, that's like that struct at the top that lists out all of our main statistics. Add that steering factor into a drift. So for drifting, there's like an additional steering number. Okay. So now we have like our steering plus our additional steering if we're in a drift gets put into here. And then our drift turning power. So whatever our drift turning power is, we're going to add whatever this turn input is, how much we're like currently trying to turn, then so we have a lot of nesting here. So take our turning input, multiply it by this. So clamp our drift control between 0 and 1 times our time factor. And then whatever that comes out to be, add it to our drifting turning power. And this itself is getting clamped. So this is going to get clamped between our negative drift max steer value to our positive drift max steer value. So whenever you see really complicated lines of code like that, you have to work from the inside out and just take it one step at a time. All right, so we were just clamping this multiplication between 0 and 1 and then multiplying it by this here and then adding it to this, and all that becomes one parameter, one input into this clamping method. All right, so vector3 dot. Now we're going to dot our rigid body velocity, normalize it. So whatever our velocity is on our physics rigid body, just normalize it down, turn it into a unit vector. Then we're going to dot it by the transform dot forward. This looks very similar. So transform dot forward, cosine. Yeah, this looks basically the same setup. Our facing velocity. So dot wherever we're currently facing, wherever our velocity is currently facing, and wherever our car is facing, multiplied by for accelerating. So if we're accelerating or not, we're going to be panning forward. If it's reverse, if we're pressing reverse, we're going to flip this into the back. And then tell me if this is greater than the cosine of that min angle. You know, so this might be like something like 0.9. Okay, anyway. This right here turns into a dot. So where's our velocity facing? Dot it with our transform, depending if we're accelerating or reversing. And if this is greater than this thing right here, which kind of evaluates to 0.9, then that's true. Then we are facing our velocity. All right, so can end drift. So sometimes you'll see this where they're declaring a variable, right? So we're declaring this bool and we're setting it equal to true. And you might be like, well, that's kind of weird. Well, it's just like creating it instead saying, okay, it's going to be true, but now we're going to go through a few situations and do some checks. And if you notice, if this is a situation, it turns false. If this is a situation, it turns false. If this is a situation, it turns false. And if none of those actually happen, it just stays true. All right, so if we're braking, then we're not allowed to possibly end the drift. If we're not facing our velocity, we're not allowed to end our drift. If our turn input absolute is greater than that killing factor, the null input, and current speed is greater than the max speed times this, the min speed percent, then this can be false too. So basically, are we allowed to end the drift? Do a bunch of checks here that would terminate, like, no, we can't end the drift this frame. And so then if we're allowed to end the drift, or our current speed gets less than like our killing speed, which happens to be really small. Basically, if we come to a stop, or we did this evaluation here and we are allowed to end the drift, then we're going to end the drift. So basically, there's no input coming from the user, and the car is aligned with the current speed direction, so we're going to leave our drift. All right, so rotate our velocity based on current steer value. I'm just going to move down a little bit because there, it looks like we're almost done. Wow, this is like a monster method. So quaternion dot angle axis. So create the rotation, which rotates the angle degrees around. Okay, so remember, quaternion is like a 3D rotation. So we're going to say, hey, we have this turning power. How much are we currently turning, left and right? Multiply it by, okay, is our local velocity dot z. So our local velocity, z, means like how much of our local velocity within our current transform, how much of that z, the forward direction, is happening. So how are we either moving forward or are we moving backward in our local space? And so that just evaluates to, is it -1 or +1? So if we're moving forward, our turning power stays in the normal direction. If we're moving backward, we have to flip. We have to like invert our turning power, or I should say negate it. And then multiply it by our velocity steering. So how much of our velocity and steering is currently coming through in our current grip. And then multiply that by how much time has passed, like a small little fraction of a second, because we're in our fixed update loop. So all of that evaluates to the angle that we're trying to figure out. And then what axis are we going to put that angle about? The transform dot up, our local up. So normally it should be like global up, but if we're like going up a ramp or we're like flipping upside down or something, you know, then that local up will be a little different. All that creates a quaternion, a 3D rotation, and it looks like we're multiplying that quaternion by a vector 3, our rigid body dot velocity, the velocity of our rigid body, which I thought you can't. Let me just look at the quaternion real quick, because I thought you can't multiply a quaternion. Yeah, usually you convert the quaternion. Okay, so this must be shorthand. So notice this whole thing evaluates to a quaternion. So quaternion.angle axis, it's going to return a quaternion based on a rotation. And then notice here, it's we're using the multiplying operator into a vector 3. So there must be, that must already be written up that you can multiply quaternion by quaternion or quaternion by a vector 3. So here it is, quaternion.operator. When you multiply a quaternion by a vector 3, you're going to get a vector 3. Okay. I've never seen that before, but we're taking our velocity and multiplying it by this rotation that's just happening, and we're setting it right back to our velocity. Interesting. So here, rigid by dot velocity, multiply it by this quaternion, and we're setting our rigid by velocity back to it. So rotate our velocity based on the current steer value. All right. Wow. So this ended some if statement. So I can that's cool. I can hover at the end of it, and it can tell me what the start of it was instead of going all like following this dotted line all the way up and saying drift if ground percent's greater than 0. We did all that, and if ground percent is not greater than 0, then we're in the air. It's true. All right. Well, that closes that if else, and let's see how much more. Okay, we're in a good state here. So, bool, valid position equals false. All right, so if they're saying to false, then they must be trying to figure out if they want to set it to true later on. So, if physics.raycast, take our current position, world position, add our local up, and multiply our up by just shrink it down. So, it's a unit size vector of size 1, and if you multiply a vector by a float, it'll shrink it. So we're shrinking it down to a tenth of the size for whatever reason. So when we're ray casting, and look, I'm guessing we're going to shoot the ray down. Yeah. Okay. So our position might at some point kind of be a little close to the ground. So to accommodate that, we're going to be shooting a ray down to see how far the ground is beneath us. So what they're doing is they're this just moves us up just a little bit. So it's just saying, hey, we're about to shoot a physics raycast down into the ground, but let's just move our starting position up a little bit just to make sure that we're above the ground and that we can do a good raycast. And where are we raycasting down? We're raycasting, take our current up and then flip it. It's saying take our transform dot up, our local up, and multiply it by -1, which means give us down, basically. Point it down wherever we're locally oriented. And the next thing that sends it to this raycast is we have to send this raycast hit in. Which normally you're supposed to create the raycast hit variable outside the method call so that you can read it later on, but they're just generating it right here. They're declaring it right here. It looks like they might not be using it. They don't care about the raycast hit information. Oh, they do. So they okay. So they're declaring, this is interesting, they're declaring this variable here as an input property, and they're just using it here within this if statement, but they don't have a need for it anywhere else. So they're just going to declare it there. These are dealing with how far we're shooting it 3 meters down. And then this is just dealing with our our physics raycasts, our layers. We don't have to think too much about this. These are like bitwise operators. I'm not going to go into that. It's not really. It's a little bit too in depth for this class, but this is just saying, hey, if the physics layer, whatever we hit, happens to be on layer 9, which is ground, 10 environment, or 11 track, then we are interested in whatever we hit. So let's just say this: if this raycast did hit, then we're going to create this vector3 lerp vector. And we're going to say, like, if we have a collision, if we're touching something, if we're like touching the ground, and our last collision normal, wherever that was recorded, if the y is greater than whatever we just hit. Okay. So whatever we last hit, it's normal, it's orientation. So the way normal, like for example, the ground is pointing up, so its normal would be pointing up. It's perpendicular. The ground is flat. Perpendicular, it would be pointing up. This part of the wall here, let me just get. So this little plane, here would be pointing up. This part of the wall here, the normal, the perpendicular to it, would be pointing this way. The top of it here, the perpendicular normal, would be pointing up like that. And for complex geometry like this, like you just have like normals on each little face pointing out perpendicular from it. But just so you understand, normal dot y is like what's its direction up? It's pointing up. And so if whatever we our last collision normal, if the y was greater than what we currently hit, needs to make sense a little bit. But if all this evaluates to true, so this here is called the ternary operator, right? So it's like saying, okay, if this is true, we're going to evaluate to this value, or else we're going to evaluate to this. And we're going to set, ultimately, this is like saying here, this vector 3 is going to be set to this or this. Basically, our last normal that we hit, or our current normal of whatever this physics hit was. So basically it's like saying if our last collision had a better normal pointing up, or more correct normal, then we're going to use that one. Otherwise, we're going to use the new one. So our vertical reference. So vector3.slurp. So we're going to do a spherical interpolation from A to B. So from our vertical reference, let's take a quick look where this was. Okay, so it's vector 3. It just defaults to vector3.up. All right. Oops. So the first time we run through this is vector3.up. And we're going to move toward whatever this lerp vector is that we just calculated, and how much are we going to move between the two. So here we have this clamp 0 to 1. So we have this airborne reorientation coefficient. Interesting. Coefficient used to reorient the cart in the air. The higher the number, the faster the cart will readjust itself along. Okay. So the higher the number, the cart will readjust itself. Let me just go take a look at this. So what's really cool is notice that there's a tooltip here, and this shows in the inspector. But notice it also shows up here. Like I was just reading it down toward the bottom. It's coming from here. So it's defaulting to 3. You can set it from 0 to 20. All right. So clamp that times fixed delta times. All right. So here we have another ternary operator. So is the ground percent greater than 0? Question mark. So if it's true, this will be set to 10. If it's false, so if we're in the ground, this is 10. If it's in the air, it's 1. Blend faster if it's on the ground. Okay. So this just ramps up to a bigger factor of size 10 if we're on the ground. But anyway, we're still clamping between 0 and 1 because at the end of the day, we're doing this slurp, our lerp, and t has to be between 0 and 1 as we're moving from A to B. Yeah, okay, so we're going from this vertical reference to slurp vector. Gotcha. And vertical reference is vector 3 dot up. So so that's only if we had raycasted successfully. If we didn't, it looks like we're resetting. We're using our previous collision, or if this is if our previous collision is not good, if it's 0 or less, we're going to reset back to up, and we're going to do the same stuff again. All right. So valid position. Ground percent is greater than 0.7. And we haven't had a collision in the dot. Let me take a look at this. So this is valid position is going to be a pool. All right. So if ground percent is greater than 0.7, okay, we're mostly on the ground, and we're not colliding, we're not touching something, and our dot of our vertical reference to the global up is greater than 0.9, then we're in a valid position. Okay. Airborne, half on the ground. So if ground percent is less than 0.7, so we're not like all 4 wheels are not on the ground. Rigid body angular velocity equals this. Okay, we're setting our angular velocity. Our final orientation direction, we're going to project on the plane our local forward to our vertical reference. And then we're going to normalize that direction. And if the square magnitude of it is greater than 0. All right. So the magnitude is just the size of a vector, and you could just square it. Whatever the size is vector, just multiply it by that size again, and it's the square magnitude. But if it's greater than 0, meaning because we're projecting it, so remember it kills whatever's not on that plane. So if our forward orientation is like not aligned with our vertical reference at all, then once we kind of normalize it, it's going to be like 0 or less. But if it is greater than 0, like we are aligned with our vertical reference, then we're going to do this move rotate. Rotates the rigid body to a rotation. Okay, quaternion dot lerp. We're going to lerp on the quaternion where our current rotation, and then a look rotation. So look rotation is kind of useful where it's like I don't want to figure out quaternion, but I'm going to say this is the forward direction, like the direction I want to look, and this is the up. You have to always specify like the axis you're like aligned or rotated with. So take our final orientation direction, orient it to our vertical reference, like pointing up. So usually when you do look rotation, pointing up is like our like we want to look around that axis. And then we're going to clamp from 0 to 1 because that's our t factor. Okay. So we're just managing. So if we're almost half on the ground or something, this is just managing our rotation of our rigid body. All right. So the details, the notes aren't that clear. But we're updating our angular velocity of our rigid body. I'm not sure why this like we're messing with our angular velocity and our rotation of our rigid bodies. Only okay, the else is a valid position. So it's like if we're mostly on the ground, we're gonna rotate ourselves in I guess like a relatively normal way, and else if we're not on the ground, like if we're greater than 0.7, mostly on the ground. If we're like, so this is saying like if one, 2, or 3 wheels are kind of touching the ground, or 0 to 3 wheels, but one of our wheels might be like off the ground, we kind of deal with rotating ourselves this way. But if all of our wheels are on the ground and we're in a valid position, then we deal with rotating ourselves this way. Oh, we don't rotate ourselves at all. We just record our position and our rotation for use later. Right. But at the end of all this, we decide if we need to activate drift VFX. So if we're drifting and our ground percent's greater than 0, okay, we have at least one wheel on the ground and we decide that we're drifting, we're going to activate our drift VFX. All right, that was big. So activate drift VFX, true or false. So for each VFX in our instances, we're gonna for each VFX, if it's active and the wheel that's associated with is touching the ground, then we're gonna play its VFX. Otherwise, if it's playing, stop it. Like the wheel is not touching the ground anymore. Cool. That was a big one. You went through awake. Went through fixed update. Power ups we haven't covered yet. Let's skip that. And we just went to that move vehicle, which is a big one. Cool. I'm going to pop out of that script because we've been living in it for quite a while. But that is the big essence of, like, that is the deepest hole of physics you will go into. Like, this is a karting game, and that was the main kart script. So I know a lot of that math and stuff probably didn't make sense. I was just kind of breaking down like the logic of each line, like what's happening, what the developer might be thinking as they're writing this. So that like you can tweak it, you can mess around with it, and you can like start to figure out what's happening with the math for each line. All right, let me just take a little look around here. So you've got kart animation, we've got kart player. So these seem to be some scripts that manage the animators. So these two we should get into. Rigid body. So that's pretty much it on the player. There's some audio script we're gonna have to look at, and probably what's going on with some of these game managers, which are probably similar to first-person shooter. How the track is pieced together. Yeah, I'm gonna have to spend at least one class just like looking at all these environmental pieces, these models, and breaking them apart. Yeah. Let me just do a little bit of planning. Right, so I got 2 classes after this, so we should spend one class definitely on the environment. All right, cool. Let me just take a quick gander at how big these other scripts are to get a timing down. Okay, it's definitely a little bit bigger than I thought it would be. Alright, so I'm gonna, next class I'm gonna take on these animators. I've got the audio. Take a look at the script. We can take a look at audio a little bit. This one probably should just be a few minutes. So, you can see Arcade Engine Audio. Looks like all the audio clips are underneath here. Each one has one audio clip, so these are all audio sources. Each game object has one audio source. And it looks like they're all kind of connected up in here. Start, idle, running, drift. And a bunch of like properties. So let's see what's going on here. So Arcade Engine Audio. So here's our audio sources, and these are a bunch of floats. And it looks like we need to know about the ArcadeKart script. So on awake, go up and get component and parent. Go up and get the ArcadeKart and update. So on update, looks like, okay, so we're setting this float to 0, so you know we're going to modify that. If we don't have our script above us, which I wouldn't even, oh, if it's not null, sorry. If it's not null, then get the local speed. So it's a method there. So if we're allowed to move, get the dot of our whatever forward direction against our velocity. If the absolute of that is greater than, so we can basically, it's like saying we can go from like negative 0.1 all the way up to 1 would be true. So get the float else. So see, so this, if this is true, we're gonna do this, so we're gonna return, and we don't even get to here. If this is false, we don't go in here, and we go here, and this returns 0. Okay. So if this dot is less than 0.1, okay, so this means like if these are almost perpendicular to each other, then we're going to return 0. If we're ever like completely 90 degrees to our velocity for whatever reason. So take the rigid body velocity, take the magnitude of that. Okay, that's our speed. That's fine. And if dot is less than 0, then flip it. Okay. So if it's not, meaning our dot is positive, we are aligned with our velocity. Take our speed, which is our magnitude of our velocity, and divide it by our top speed. So it's some percentage between 0 and 1. And if dot is negative, take our speed divided by our reverse speed, because we're going in reverse, and then flip and give us the negative of it. So it'd be something negative between 0 and negative 1. All right. Else, if we're not allowed to move. Okay, so this is like if we're waiting, and we're like revving up. If we're pressing accelerate, then pass it a 1 or 0. So play the sound or not if we're accelerating before the game starts. That's interesting. In either case, this returns back something between 0 and 1. And then if we're drifting and our ground percentage is greater than 0, then this will be taken. Take our velocity magnitude. Otherwise, if we're not, take I'm sorry, take this divided by our max speed, otherwise 0. So this just changes if we're in a drift state or not, how we're going to mess with the volume on. And we're going to lerp up the volumes. So let's see, all right, we got a few more minutes. So math F lerp. So go from 0.6 to 0 based on our cart speed times 4. Okay. So this cart speed, as I said, is going to be between 0 and 1. And lerping is usually 0 to 1. I don't know why they're going past, because it breaks at 0. But basically, they're ramping up faster. So we're going to go from 0.6. Oh, the idle sound. I see. The idle sound drops super fast. Like it's at, if you're idling, it's going to be playing at 60%. Any type of speed coming in is going to quickly drop it down to 0. And that's just the volume of our audio source. So then if cart speed is less than 0, okay, I'm sorry, cart speed would be -1 to 1. So if it's in a reverse situation, our running sound is set to 0, and our reverse volume will be lerping up from 0.1 to whatever the max is. And you take that cart speed, you have to flip it back because it needs to be positive and multiply by 1.2 just to make it lerp quicker based on how much your reverse of the volume will go up. And the pitch is like how increasing like the height of the sound waves, making it a higher frequency, making that like it'll go from a low pitch to a high pitch, like that. So your reverse sound kind of raises in pitch based on how quickly you're putting on the foot pedal. And so we have to flip the speed again because it's negative. So we get back to positive, and then okay, it's sine. So it's fluctuating. It's going up and down from -1 to 1. Yeah, you put in a time value, and it'll just like keep running through the curve. So it's going to be going up and down based on time. And then we're just multiplying that by 0.1. We're just shrinking it. The effect of it, we're making it smaller. It's going to be from -0.1 to 0.1. And then we're just adding that to whatever our cart speed, which would be so it would be something higher, maybe something like 0.8, 0.9, and it's going to fluctuate. So it's going to make that's what makes that, it's that engine noise is like oscillating. This is what's doing it. So it's making the pitch change from like 0.6 to 0.7 to 0.8 to 0.9, back down to 0.8, 0.7, 0.6. That's what's making this pitch oscillating as you're reversing. And moving forward, it's much the same as I can see here. So that's the one interesting here is how it's oscillating the pitch to make that engine like fluttering, oscillating noise, and it's doing here with the sine wave. So you'll see this type of stuff. It's multiplied by the running time. It doesn't matter if this time just keeps getting bigger and bigger and bigger because it's just going around a circle. It's just how many times you're going around that circle. At the end of the day, the y value is still just going to go between -1 and 1. And then it's just shrinking it down to a range of -0.1 to 0.1, and then oscillating it around our speed value, whatever that happens to be, something like 0.8. So cool. A little bit of sound engineering. So it's cool to look at that. And with that, I am done. And we're going to have to look at the animators and in the environment. And let me just write that down. And let me know if any questions. Otherwise, you're free to go.